Today, we'll discuss about diagonalization. There is a process of diagonalization. That is, given a matrix A, square matrix A, how to diagonalize it, right? First of all, you need to understand when are two matrices said to be similar? Two matrices, A and B, of course, square matrices A and B of order n, they are said to be similar matrix if there exists another matrix P, right, which should be non-singular, such that one can be expressed in terms of other through that non-singular matrix P, such that B equal to P inverse AP. Then A and B are said to be similar matrices. That is, if B can be written as P inverse AP, right? Where P should be non-singular, because then only P inverse exists. Then only it's possible. If such thing happens, then we say that A and B are said to be similar matrices. What is the advantage with similar matrices? Of course, similarity is an equivalence relation. Right? Similar matrices will have the same determinant. So they will have the same characteristic equation. That is the same characteristic polynomial. Hence, they will have the same eigenvalues. Right? If x is an eigenvector corresponding to an eigenvalue lambda, then P inverse x is an eigenvector of B corresponding to an eigenvalue of lambda corresponding to a matrix A. Right? So our goal is to develop a useful factorization A equal to P D P inverse, where A is a given matrix, n by n square matrix, and we have to find P. That P we call in future as a model matrix, and ultimately we want to find for a larger K, we want to find the powers of K. Of course, K should be positive integer, and the matrix D, which is a diagonal matrix, right? What is the advantage? If A is diagonalizable, then calculating A power K is easy. Of course, calculating A power K depends upon D power K. D is a diagonal matrix, right? Right. Now, a couple of properties we use in future. We have seen in the last class that if A is a square matrix of order n, and if it has n distinct eigenvalues, then with the help of those eigenvectors, I can have a basis. Right? Similarly, if A happens to be a symmetric matrix, its eigenvectors form an orthonormal basis. Basically, they form an orthogonal basis. Once it's an orthogonal basis, constructing orthonormal basis is not a big deal. Right? If the eigenvalues are repeated, A is a general matrix, if the eigenvalues are repeated, then their corresponding eigenvectors may or may not form a basis. It goes case by case. You have to really inquire that. Right? Just a quick recap. Two matrices A and B are said to be similar if there exists a non-singular matrix P such that A equal to P inverse AP, and similar matrices will have same eigenvalues. Right? Let's see the process of diagonalization. A matrix A is said to be diagonalizable if it's similar to a diagonal matrix. Meaning, we need to find the model matrix. Right? B, we call it as B. If a model matrix B exists, then we'll calculate B inverse. Then B inverse into A into B will be a diagonal matrix. Right? Now, the issue is how to find that B inverse. Given A, how to find that B inverse. For that, I need to find the model matrix B. So, given A, how to find the model matrix B? Once you have a B, then B inverse, if it exists, then B inverse into A into B will be the product of these three matrix will be a diagonal matrix, right? So if A is a square matrix of order n, and if A has n linearly independent eigenvectors, then we are going to construct the matrix B taking these n linearly independent eigenvectors, right? Then B inverse exists, then B inverse into A into B will be a diagonal matrix, right? So B is called a model matrix, right? Let's see a couple of examples. If A equal to 1, 3, 2, minus 4, note that A is not a symmetric matrix, right? We'll find its eigen. We have seen that how to find eigenvalues and eigenvectors in our last class. Suppose its eigenvalues or lambda 1 equal to minus 5 and lambda 2 equal to 2. We'll find the corresponding eigenvectors. Suppose the eigenvectors are 1, minus 3 and 2, 1. Then we construct a model matrix P as taking these eigenvectors as columns. Say first column is 1 minus 3 and second column is 2 1, right? Then P inverse do exist. P inverse equal to this. You can use either a MATLAB or you can use hand calculations, right? P inverse is given by 1 by adjoint of P into right, 1 by det A, 1 by det P into adjoint of P, right? Then find the product of these three matrices, P inverse into A into P, right? If you find the product, you can see it will be a diagonal matrix, right? And the diagonal elements happen to be the eigenvalues. So given a matrix A, find its eigenvalues and eigenvectors. Its eigenvalues go as diagonal elements and then eigenvectors are used in the construction of the model matrix P. Right? Let's take another example. A equal to 1, minus 1, 2, 0, 2, minus 1, 0, 0, 3. Right? Find its eigenvalues, eigenvectors. Then we'll find the model matrix. Then we'll diagonalize it. Then we'll make use of the advantage of diagonalization. Then we'll find the A cube. Right? Now, take the matrix, form its characteristic equation. Right? This, when expanded, is a polynomial, cubic polynomial. It will have 3 roots. Find the roots, say lambda equal to 1, 2, 3, they're all distinct. And find the corresponding eigenvectors. How to find eigenvectors? Solve the homogeneous system A minus lambda I equal to 0. Take lambda equal to 1. That leads to this coefficient matrix. Rank of this is 2. So I can have one free variable. So I express everything in terms of x1. Right? So I take x1 as a k, and I know x2 is 0, x3 is 0. So x2 can be written as a 0k1, and x3 can be written as 0k1, and finally the eigenvector, the eigenspace corresponding to lambda equal to 1 is given by k times 1, 0, 0. So an eigenvector, I'll pick one from that, an eigenvector corresponding to lambda equal to 1 is a 1, 0, 0. Right? Similarly, take lambda equal to 2. You get this coefficient matrix, right? And rank of this coefficient matrix A minus 2i is a 2. So I can have one free variable. I take x1 as the free variable. Then I'll express everything in terms of x1. Then finally I get x2 equal to k2 times 1 minus 1, 0. I take k2 equal to 1. So x2, an eigenvector corresponding to lambda equal to 2 is 1 minus 1, 0. Take lambda equal to 3. Then A minus 3i is the coefficient matrix. Take the coefficient matrix. Rank of this matrix is 2. Right? Here, I can take one free variable. I take, just for a change, I take x2 equal to a free variable. Take x2 is a constant. No rule, you can take a whatever you want. Right? X2 equal to k3. Then x3 we know it's a minus x2, so it's a minus k3. The next one I can speak in terms of k3. Finally, x3 will be k3 times 3 minus 2, 2. K3 I'll take it as a 1. So finally x3 is 3 minus 2, 2. Right? Now I take all these three eigenvectors. I construct the model matrix, a B or a M or a P or whatever. Different textbooks takes it, but standard notation is a P. Some they take as a M. Here in this example, I've taken as a M. So taking those eigenvectors as columns, I construct a model matrix. Det M is equal to minus 2, which is not equal to 0. So M inverse exists. So M inverse is 1 by det M into adjoint of M. Right? Calculate the inverse. Then take the product of these three model matrix, its inverse, and so that is M inverse into A into M. Now the product of these three matrices is nothing but 1, 0, 0, 0, 2, 0, and 0, 0, 3. Look, the eigenvalues goes as the diagonal elements. This is my diagonal matrix D. Right? This is how I diagonalize. So what I've done, taken the matrix A, I want to diagonalize that, mean reduce it to the diagonal matrix. Take the eigenvalues of A, lambda equal to 1, 2, 3, take its corresponding eigenvectors, right? You got the eigenvectors. Then construct the model matrix M, taking M or B or P or whatever. By taking these eigenvectors as columns, then find M inverse, and the product of M inverse into A into M will be a diagonal matrix, right? So M inverse into A into M will be a diagonal matrix. So I pre-multiply both sides. I pre-multiply both sides by M inverse, sorry, M, right? Then I post multiply both sides by M inverse. So finally, I get A equal to M D M inverse. Then A square equal to this into this. Do some simplification. Finally, A square equal to M D square M inverse. And in general, A power K equal to M D power K M inverse. Right? Whatever, it's the product of just three matrices, M, D power K, and M inverse. So here in the discussion, it's A cube what we want. So A cube equal to M, D cube, M inverse. So plug in all the matrices, and D cube is nothing but, we have seen in the properties of eigenvalues and eigenvectors. So D cube is 1 cube 0, 0, 0, 2 cube 0, 0, and 0, 0, 3 cube. Right? Now, product of these three is a cube equal to 1 minus 7, 32, this. That's how we calculate A cube. So, what we have discussed is how to diagonalize a matrix, and making use of that diagonal matrix, how to find the powers of a matrix A.